Good evening, everyone. And firstly, I'd really like to thank you. I am privileged and honored to be here tonight, and I'm especially pleased that you've given up your Saturday evenings to go on what I hope is a voyage of discovery, a voyage maybe of enlightenment, but ultimately a voyage to answer the deliberately provocative question, space, so what? Now, I know I've got a different version in my title slide in terms of what we're going to be going through, but over the next hour or so, I want to try to give an insight into why it is, in spite of space being inspirational, why we are prioritizing it so much when we have so many challenges here on the surface of Earth. The lecture part, which includes a few demonstrations, it should last an hour, maybe an hour and 5 minutes, which gives plenty of time for questions and answers. The last thing I want to highlight, I'm here in my full-time role with the United Kingdom Space Agency. I have a couple of other roles as well with the Research Councils and an academic role, as you can see on the title slide. Any opinions I express this evening, and there might be one or two, they are most definitely personal ones and not institutional ones. But I want to set the scene by reminding us of how close space is to where we are now. Because the internationally accepted boundary of space, it's not thousands of miles away, it's not light years away, it's only 100 kilometers. That's 62 miles in old speak. Space is closer to where we are all sitting now than the distance I have driven this afternoon, coming with all my kit from Stratford upon Avon. So space is incredibly close to us, but we've got to remember that when we're thinking of going into space, we're battling against gravity, a force that's dominated the way that life's evolved on this planet for billions of years. And if we want to stay in the space environment, then in terms of radiation, in terms of temperature, in terms of atmospheric pressure, this is a far more challenging environment than we find anywhere naturally on the surface of our home planet. So have no doubt about it, we've been doing space stuff for more than 60 years, but it is still pushing our science and our engineering to its very limits. But when we get there, the view is literally breathtaking. What I'm sharing with you is photography taken from the International Space Station at an altitude of 400 kilometers above the Earth, and we're looking at night passes of our home planet. The view is absolutely magnificent. We can see the interactions of lightning storms separated by hundreds of kilometers but electromagnetically linked. The view is dreamlike, but we are falling around the Earth on a path in which in 1 second we're covering a distance of nearly 8 kilometers. And every 90 minutes we have that transcendental experience of orbital sunrise. We can see Orion, the constellation, rising above the rim of the Earth. From up there, you have an almost unobstructed view of the universe around us. And here on this path, flying over Europe, see Italy on the right-hand side, we get a totally different perspective of our home planet and of human development as we see an explosive expansion of wealth marked out by city lights in so many parts of the Earth. And of course, as a physicist, I love this because I've got a living physics lesson when I'm looking at the interaction of the solar wind being funneled by the Earth's magnetic field to interact with our upper atmosphere. So it's little wonder that whenever we see imagery like that, not only does it captivate and beguile us, but so many of us would want to have that experience of being an astronaut. I said it wasn't easy, and one of the biggest challenges we have are the energetics of getting into orbit, which, if you're close to Earth, is that speed of 18,000 miles an hour, 5 miles or 8 kilometers every second. And what I want to do next is to illustrate with you one of the major challenges we face in terms of rocket propulsion. Now, I'm here in the Royal Institution, and I had prepared a demonstration earlier, but then I realized I cannot put by the opportunity to show you this demonstration for real. And what we're going to have is a demonstration of the technology, the chemistry that's behind every single rocket that has successfully or otherwise been used to put a satellite into space. The demonstration will take a few minutes, and what I'll do is I'll narrate through the various bits and bobs that we have. First of all, if we want to have a rocket, we need to have a high-energy exothermic chemical reaction. That's a chemical reaction that gives out lots of energy. And if we can use that energy to blast out gases in one direction, then by Newton's laws, we'll have a reaction in the other direction. And that's how every single rocket works. So what we're going to do to simulate our rocket motor here is I've got what we call a whoosh bottle, which is just a normal drinks container, a very large drinks container. And what I'm going to use for my fuel for this demonstration is I'm going to be using ethanol. And so what I have here, this is actually bioethanol. And for this demonstration, you know, I'm building this up, but you're probably going to be disappointed because I'm only going to use 20 milliliters of ethanol. So pouring this out and having quite a big delta there because that's a bit more than 20 milliliters. Never mind. Let's just whack it in. Going to pour in the ethanol. Now, that ethanol is full of chemical energy that's just waiting to be released. But to unlock it, I need an oxidizer. And in this case, the oxidizer is going to be oxygen from the air that is in the bottle. Now, what I'm going to do for the demo is, this isn't the case with all rockets, of course, but for this demonstration, I'm actually going to vaporize that ethanol. And the way I'm going to vaporize it is I am going to agitate this bottle for about a minute. And while I'm doing that, so the ethanol is going to change into vapor, I'm going to talk a little bit about the history of rocketry. So sorry I'm stalling for time while I seal this up. This is a demonstration I think many of you may have seen before. Okay, now I'm going to agitate this, shake it around for about a minute or so, and just explain a little bit about the history of rocketry and the type of rockets we have. So what I'm now doing is just vaporizing that ethanol. You know, we think of rockets very often as being a modern technology, and of course they're not. They date back hundreds of years to solid rocket fuels that were used in China as fireworks, and then, of course, through the various iterative types. Now, rockets come in all sorts of shapes and sizes. Some of them have got solid fuel, like fireworks. Now, solid fuels are great. You know, they might have aluminium perchlorate as the mixture in there. The thing about solid rockets, though, is that once you start them, it's very hard to actually stop them. And so the alternative is to use liquid-fueled rockets. And liquid-fueled rockets are brilliant because you can turn the flow on, you can turn the flow off. However, for the fuels that we're using in normal rocketry, the volumes of material or the mass of material we need would mean that if they were in a gas form, the rocket would be too big to launch. So what we've got to do is we've got to cool down the fuels that are used. And some fuel mixers might be kerosene and oxygen. Well, kerosene is straightforward, but oxygen, to liquefy it, you've got to cool it down to about minus 170, minus 180. If you want to use liquid hydrogen as your fuel, you're cooling down to minus 250 or thereabouts degrees centigrade. So you can start to see the challenges that we have already. Now, I've been agitating this for 30 seconds. There's still a bit of liquid ethanol left in there, so I'm going to keep shaking. I'll time myself for about 15 more seconds. And just as a reminder, what we are going to see in effect is this bottle being used as a rocket combustion chamber, because you can have your fuel and your propellants, so your oxidizer and your fuel, in one part of the rocket, but it's only when they come together that you unlock all of that chemical energy in your exothermic chemical reaction. And I'm hoping I've not got any leakage from there. Okay. Now, for this demonstration, the part that very often people forget is to pour out the ethanol that has not vaporized. Now, I said I poured in about 20 milliliters in there, but you'll see that it's not all vaporized. So if I pull this off, we've still got some ethanol that is a liquid. So I've probably only vaporized maybe 10 mils of ethanol. Surely we can't get a dramatic demonstration with that tiny amount of fuel that's in there. Well, what we now need to do is to initiate the chemical reaction. And if I could ask for the lights to be dimmed, please. Okay. Everything went right there and everything went wrong just there. Okay, thank you. And just to show you again, we'll now go to the slide. Thank you very much.
Three, two, one.
And so for any rocket combustion chamber, when the exhaust products are ejected at high velocity in one direction, we get a reaction force. We actually get a change of momentum, an impulse in the other direction. And as long as that rocket is firing, we'll get those continual impulses. That's how you get your thrust. Now, that's what happens with a tiny amount of fuel. What did I say? 10 to 15 milliliters. What about real rocket engines? Well, I want to go forwards now to a picture from about 12 years ago when I was slightly less follically challenged than I am at the moment. This is me at the business end of the largest rocket engines that have ever successfully, to date, been used. These are the F1 engines on the Saturn V rockets that were used in the US lunar program. And to give you an idea of scale, well, you can see me there, each of those engines was using 3 tons of kerosene and oxygen every second. Now, that's the largest rocket that's ever successfully been flown, but of course, we have new developments. And of course, for the largest ever rocket that's been launched, if you've been following the space program, you'll know about Starship. And I want to show you the footage from the latest Starship launch that really puts things in perspective and explain a few more of the issues we have with all rockets.
Attention all operators on countdown 1. This is the final go, no go for flight 2 of Starship.
This is an absolute monster of a vehicle. 392 feet high, liftoff mass in excess of 6,000 tons.
Stage 1.
Go.
Stage 2.
Go.
Copy, go for flight.
This is at Boca Chica, on the border
10,
of the US and
9,
Mexico.
8, 7, 6, 5, 4, 3, 2, 1. We have liftoff. Nobody was within 3 miles of the launch pad in case of a catastrophic anomaly at liftoff. Now, every rocket we build, we have an enormous ratio of how much fuel you need to how much you can put into space. Here we've got staging, second stage firing. That entire massive complex is designed to be reusable. You can see the first stage flying back to Earth. But that is to put less than 10% of its liftoff weight into Earth orbit. And if you've been following SpaceX's journey, you'll know that while there were successes, there were failures. But as we always do in rocketry, you learn from your failures, you iterate for future successes. And the next test flight of this system will probably be in February of this year. Now, very often, when it comes down to thinking about space, we think about astronauts. But when people ask me the question, Anu, what do you mean by space stuff? To me, it's very, very simple. It's 3 things. There's looking out there, astronomy. There's going out there, so this is exploration and with humans. And then finally, there's the side of space that so many people overlook, be they general public or even policymakers and politicians. It's the satellites that aren't looking out there, but the satellites that are looking back here. This is space for the benefit of life on Earth, the world of satellite applications. And what I want to do now is go through each of these categories and just show you what difference I have seen within my lifetime. And I want to start with astronomy. And specifically, I want to start with Christmas Day 2021. So what you're seeing is a visualization of the launch of the James Webb Space Telescope from Kourou in French Guiana, a combined NASA, European Space Agency, and Canada project that has deployed the largest space telescope ever built into Earth orbit. To give you an idea of scale, the sun shield that you can see deploying is the size of a tennis court, and you can see that massive mirror assembly made of hexagonal elements, okay, that dwarf the Hubble Space Telescope. And this telescope is not located close in Earth orbit at 550 kilometers like Hubble. It's 1.4 million kilometers away from the Earth at the Earth-Sun Lagrange 2 point. Now, Hubble transformed our understanding of the universe, and James Webb is already doing that. And I want to share you a few of the images that have been returned within the last 2 years as a montage. So Hubble and James Webb, when we look, for example, at the second of those images and the third of those images, they've effectively shown us, you know, the past of our solar system and the future fate of our solar system. On the left-hand side, you can see the Carina Nebula, a region where new stars are being born. In the third image, you can see the Southern Ring Nebula, NGC 3233. This is what happens when a star, similar mass to our sun, ends its life after billions of years and puffs off its outer layers to form a planetary nebula. On the right-hand side, you can see Stephan's quintet of galaxies in exquisite detail. And never forget, you know, a galaxy is a collection of hundreds of thousands of millions of stars, many of them like our sun. But to put the context on the left-hand image, this is a patch of sky that has got the astronomical designation SMACS 0723. And the image I'm going to show you is a patch of sky which, if you were holding a grain of sand between your finger and your thumb and you extended it 1 meter from your eye, that is the size of sky that you are looking at. Now, the James Webb Telescope looked at this patch of sky for 12 hours, catching more and more photons, and what emerged was this image here. You are looking at an image of thousands of galaxies. And that's in that tiny patch of sky. You can see evidence of gravitational lensing. In fact, I could do an entire lecture on this image, but we haven't got the time. The point I want to bring home to you is that you can use A-level mathematics, even GCSE-level mathematics, and this image to prove once and for all that with those 10,000 galaxies, each with hundreds of billions of stars in that image, covering that tiny fraction of sky, there are more stars in the universe than there are grains of sand on all the beaches of planet Earth. So the astronomy we have done from the ground and from space have transformed our understanding of what our place is in this vast, beautiful, and dynamic universe. Next, I want to move on to exploration. But in order to understand exploration, we need to look at the geopolitical drivers for why we went into space, because it wasn't idealism. It was Cold War politics. And having lost rounds 1 and round 2 of the space race, in other words, launching the world's first satellite, which the Soviet Union did, Sputnik 1, 1957, and then launching the first human into space, Yuri Gagarin, in April 1961, the US knew that they had a massive amount of geopolitical pride at stake. And this is why President Kennedy set that bold, audacious challenge in the early 60s to send Americans to the moon and back within a decade. Now, when it comes down to the moon, very often we take for granted the moon in the night sky. So what I've got here is a lovely data set taken by Deep Space Climate Observatory that you can see there. It's not an animation. I've got a diagram showing a usual textbook picture of the Earth and the moon that we see in textbooks or we see online. This one's from Encyclopedia Britannica. And what I've got there is some mathematical data about the Earth-Moon system. Now, the thing is, Mathematics is telling us a story, and very often as a visual species, we are misled by diagrams that we see. What I have scrubbed out there are the really tiny words, not to scale. What I want to do now is bring home the reality of what the language of mathematics is really telling us. Now, my assistant, who's come up from me from Coventry today, is my nephew, Rohan. So can you give him a round of applause, please? Because he didn't know this morning that he'd be helping me. Honestly, I told him about 2 o'clock this afternoon when I picked you up to bring you here. I said, by the way, Rohan, you're going to be my assistant today. And he's like, absolutely fine. He is going to university to do physics. I haven't been doing a sort of like an inside job on that. So I'm very, very pleased you could join us here, Ron. Now, what I've got here, just to explain the context, is I've got my Earth. Now, the Earth-Moon distance does vary because the Moon's orbit around the Earth is elliptical. Technically, I know that they're actually both orbiting around their common center of mass. Let's not go into those details. But roughly speaking, the Moon's orbital distance from the Earth is 10 circumferences of the Earth, very roughly. So I've wrapped a piece of string around here 10 times. This is the Moon with the correct scale compared to the Earth. It's about the same size as Australia or Canada or China. Take your pick, about a quarter of the diameter of the Earth. Now, that's correct in these images here, but you can see the distance is all wrong. So having wrapped this piece of string around here 10 times, all I'm going to do is ask Rohan, if you can come here, please. Hold the Moon, hold the end of the tether, and as we say in spaceflight, we will deploy this tether now. Now, start moving backwards, please. And if you stop there, that's the sort of visualization we get from this image. But, you know, there's a lot of string left here. So I think, Rohan, you need to keep going, please. Just go carefully, because you go up the stairs, so we can make sure you keep in camera angle. And if you haven't seen this demonstration before, I hope you are, to some degree, surprised at what the language of mathematics is actually telling. Keep going. Keep going. I'm not trying to get rid of you. It's the maths, and it's the scale of our universe. Right. We are now at full extension. This is the true scale of the distance to our nearest naturally occurring neighbor in space. How far away did I say the international boundary of space was? Excellent. 100 kilometers. Everyone shout that out. That's 1 millimeter on this scale. International Space Station, ISS, 400 kilometers, a finger width. The Moon is 1,000 times the distance to the orbit of the International Space Station. And if we go to the next nearest planet, which is Venus, we are talking about a distance more than 100 times this distance. So we start to see the challenges that we are facing in directly exploring even our own solar system, let alone the universe. Thank you very much, Rohan. Can you give him another round of applause, please? As I say, I volunteered him into it. Okay. So having visualized that distance, and if I remember where I've put my clicker down, this is one of those things where I always do this. I think faster than I do things. I just want to summarize the successes of Project Apollo. You know, between 1968 and 1972, I think of them as 4 magical years. Because the 24 human beings who went to the moon during Project Apollo, starting with Apollo 8, December 1968, and finishing with Apollo 17, December 1972, they became the only members of the human race to directly explore an alien world. You can see an image from the Apollo 15 mission, arguably the most beautiful of the landing sites, Hadley Apennine, in the summer of 1971. On the right-hand side, you can see imagery that was taken decades later from lunar orbit by a spacecraft called LRO, Lunar Reconnaissance Orbiter. And what I want to share with you in this image set is the fact that with no atmosphere on the moon, there's effectively no dynamic erosion. The only erosion you get is from micrometeoroid rain that will take millions of years to get into effect. And so whatever we do to ourselves here on the ground, you can see the footprints. You can see the tire tracks from the 3 lunar rover missions and also from Apollo 14 and the little lunar wheelbarrow that was being dragged around. Humanity has left its mark on the cosmos because those footprints and tire tracks are going to maintain their integrity for millions of years. And a question I'm often asked is, well, why did we stop going to the moon just as we got good at it and the science yield was going through the roof? It's a complex argument to do with economics, to do with geopolitics, to do with positioning, and to do with public opinion. But in a nutshell, the US changed its prioritization to try to bring down the costs of accessing space, because the space shuttle that was developed in the 70s and started flying in 1981 was meant to be partially reusable. Because with your traditional rockets, you build them once, you launch a tiny payload at the top into space, and you build a brand new rocket. It's a little bit like saying every time you go on an airline on holiday to France or Spain or Italy, you're building a new airliner. So the space shuttle was an attempt to actually reduce the cost of access to space. And from the Soviet Union's perspective, having lost the race to the moon, they became masters at building space stations. And this is the crown glory of the old Soviet space program. This is the Mir space station docking with the space shuttle Atlantis in 1997. I never thought I would have seen this when I was a child. You know, a Soviet space station. I grew up at the tail end of the Cold War, docking with a US space station. And of course, recent events have shown that geopolitics can change very, very quickly. Nevertheless, it was this collaboration that led to the International Space Station Partnership that we see now. This enormous 500-ton structure in space that was assembled with separate components on more than 30 separate missions. There, you can see the scale of the ISS. I said it was 500 tons. First assembly flights were flown in 1998. It is the size of a football field. And since the year 2000, it has been continually occupied by rotating groups of astronauts, or from the Soviet Union and Russia, cosmonauts, it's just their word for astronauts, without a break for more than 2 decades. So for the lifetime of your lifetimes, for many of you as younger members of the audience, humanity has continually been an off-world species. Now, in terms of why we built the space station, it is to conduct world-class science in Earth orbit in an environment that we cannot replicate for long periods of time on the surface, the environment of microgravity. And to date, we've had more than 3,000 investigations conducted on the ISS with participant scientists and engineers from more than 120 countries. And of course, those astronauts and cosmonauts, they've got to keep themselves alive, they've got to keep the space station alive, and they've got to do the science that they're tasked with doing. Hundreds of experiments on each what we call increment, or 6-month expedition. Now, the favorite place for everyone to hang out on the ISS is its control tower, which is called the cupola. Here we can see Jessica Watkins, a NASA geologist, on her mission 2 years ago, spending 6 months up there. I fully expect to see her on one of the first lunar missions, and we'll come back to that a little bit later. And of course, the United Kingdom has been involved in human spaceflight for a long time. On the left, I've got Tim Peake, who I'm privileged to say is a colleague. I worked on his mission and also a friend. This is the magnificent selfie he took on his EVA on his spacewalk. But never forget that Tim wasn't the first Briton in space. The first Briton in space flew 25 years earlier. It was Dr. Helen Sharman flying on the Mir space station in 1991. Now, when it comes down to human spaceflight, yes, it's inspirational, but it's also incredibly challenging. And what I want to highlight now in my next demonstration is one of the biggest challenges we face. It is, how do you keep humans alive in an environment where you might lose atmospheric pressure? When we're here on the surface of the Earth, we tend to forget that we're living at the bottom of an ocean of atmosphere that's extending above our heads for hundreds of kilometers. And the reason why we feel what we call atmospheric pressure is the weight of that atmosphere above us. Now, I promise you're not going to have a physics lesson, but we might have some physicists. I know we've got a proto-physicist, well, a physicist already, but not yet at university level. So if there are any physicists or chemists or scientists here, I have thrown a few equations up there. Don't be intimidated by them. What they are telling you as a story, actually, there's several sides to it. First of all, that figure of what atmospheric pressure is in either millibars or kilopascals, what it means is that on every square meter of the Earth's surface at sea level, you've got the weight of a column of atmosphere of 10 tons. And that's pushing in on you in all directions. And the only reason we're not completely squashed flat by that is that we're internally pressurized with gases ourselves that are pushing outwards. Now, as you go above the surface of the Earth, the pressure gets lower and lower. And that makes sense, because you've got less of a column of atmosphere above you. And you can see it's an exponential curve. But what that means is that if you go higher and higher in the atmosphere with your internal pressurization staying the same and the external pressure getting less, you're going to start to get swelling of tissues. You're going to start to get gases trying to explosively outgas from your lungs. And that means things get very, very challenging. So the reduction in pressure means that gases are going to try and escape more and more from your body. But there's a more insidious factor that we need to deal with as well. And to show that, what I've got here is I have got a kettle of very hot water, but it is not boiling. And we all know that down on the surface of the Earth, water boils at 100 degrees centigrade. What I've got here is just a glass syringe as a demonstration syringe. And what I'm going to do is I'm going to extract some of that very hot water. It's not boiling. And I'm going to leave a tiny airspace above. Now, there is no way I can add heat energy to this system. That water's probably at about 60 degrees centigrade at the moment, and it's not boiling. But if I seal the top, and if I pull down, you can start to see, it's almost magic. I want to check that it's showing on the camera. You can see that this is now boiling away quite furiously, because if I lower the pressure of a gas above a liquid, I'm reducing the boiling point. In fact, for any purists here, what you're actually seeing there is a combination of boiling and also gases coming out of solution. And the moment I equalize the pressure, it stops. So the boiling point of water depends upon the atmospheric pressure above it. And as you go higher above the Earth, atmospheric pressure gets less and less and less. And I said that the internationally accepted boundary of space was 100 kilometers, but the aeromedical boundary of space is only 20 kilometers up, 63,000 feet. Because if you go up to an altitude, 63,000 feet, that's the height that Concorde used to fly at, the boiling point of water reduces to 37 degrees centigrade. And I think we can all see the relevance of that when it comes down to the major constituent of the human body. What this means is, if you're flying at 60,000 feet, I do apologize. I tend to be, I'm a bit old. I was born in 1968. I'm very much a sort of imperial mindset generation at the transition to metric. So yes, I can work in meters, but I tend to think in feet. I apologize about that. 63,000 feet, if you are exposed to that low pressure environment, you need a full pressure suit to survive. Now, when it comes down to these low pressure effects, I have got a little bit of myth busting in the slide, but before I do that, a visualization of what's happening in terms of that boiling point of water. If you have lots of air molecules above a liquid, the molecules in the liquid phase that are moving quite slowly, rolling over each other, every now and then one of them escapes, you get evaporation, but generally they are held down. If you start removing those gas molecules above, it becomes much easier for the water molecules in the liquid phase to escape. So that's a simplification of what is going on with the reduction of the boiling point with atmospheric pressure. But in terms of what would happen if you were exposed to those incredibly low pressures, you know, some people think your blood's going to boil in your veins, or some people think your body's going to explode. Actually, human tissue is quite elastic. You're not going to explode. And your arteries are actually very good at withstanding differences in pressure. So your blood is not going to boil in your arteries and veins. But what we do know from pressure chamber accidents that have happened is that it's going to be pretty nasty for you, and you've probably got life expectancy of less than a minute, and you'll probably lose consciousness in 15 seconds. The explosive outgassing of gas would probably, and has done in pressure chamber accidents, cause damage as teeth have been blown out. You would get shredding of the alveoli in your lungs, and you'd lose consciousness, and you'd get massive edema within 15 to 20 seconds, as well as a catastrophic case of the bends as the nitrogen gas dissolved in your bloodstream comes out of solution. So there's some myths, there's some reality. You need a full pressure suit if you are going to be exposed to that low pressure environment. And we know this because tragically, this has happened in spaceflight. Some of you may have seen, I've got my UK Space Agency pin on, and I've got another pin on here. This pin is commemorating the crew of the world's first space station, Salyut 1, the crew of Soyuz 11 in 1971. They occupied the Salyut 1 space station for 23 days. They were heroes in the Soviet Union. They got into their return capsule, their Soyuz capsule, which re-entered the atmosphere, parachutes deployed, landed in Kazakhstan, absolutely safe. The recovery crew went to open the hatch, and the crew were dead because they hadn't been wearing pressure suits and there had been a loss of pressure during their re-entry to Earth. So the reason why this pin, and I've shown the picture on the left, was actually taken up to the ISS was to commemorate that crew, because that crew's sacrifice is what's led to so much more survivability that we now have in the human spaceflight program. And that's the reason why, for launch and landing, every astronaut or cosmonaut now will be wearing a full pressure suit. And what I've brought to show you here is a pressure suit, one of two different models that was developed for the Soviet Union's Buran space shuttle program. There's the STRIS pressure suit on the left, and there's STRIS HAV on the right-hand side. And we actually have an example of it here. When you take off the outer covering, that's what it looks like underneath. The European Space Agency did evaluate this model in the early 1990s, potentially for use in a project where Europe was looking to build its own space plane called the Hermes space plane. That project came to nothing, but I'm delighted that we can actually show you a genuine high-altitude stratospheric suit here. There's a few features that I wanted to highlight that all spacesuits have in common. You've got to have an assembly that's going to be airtight, and you've got to have an assembly that's going to allow you to move your hands, to have some degree of motion. Now, for this particular helmet, the visor, the external visor here, which is designed to filter out very, very high levels of ultraviolet radiation, I'm actually going to remove it so you can see the demonstration a bit more easily. And this particular one has also got integrated risers, because this was actually designed for stratospheric ejection as well. So if something went wrong with Buran on its ascent into orbit or its return during re-entry below a certain altitude, the crew would have a chance if they actually were to punch out. And so later on, you can have a closer look at this particular suit, but what I do want to highlight is just how different it looks when we pressurize it. Because pressurizing a suit leads to radically different characteristics. And so what I'm going to do now, I'll apologize about the noise. In a real spacesuit pressurization, this would happen in a fraction of a second. But I think you can see it's quite dramatically changing in its appearance. It's almost as if there's a mannequin in there. And now, and sometimes people get a bit spooked by this, you know, if I sit this particular one up, you know, I have had one or two people going, where's the person? Where was the person hiding who's in there? You can start to see the profile. Now, it's a little bit of fun, but we've got a serious point here, because if I feel it, it's quite pressurized, and therefore, if you're going to be using it and moving in it, you're going to be needing a lot of muscular effort, and so you've got to have a lot of ways of thermal regulation in these suits, let alone the ability to try to facilitate movement, and of course, to have a constant oxygen supply and somehow removal of that carbon dioxide that's going to build up. So you can start to see now the challenges we have just in terms of pressure suit technology. Now, we've still got a lot to get through, so what I'm going to do is I'm going to leave my colleague up here, and you can have a closer look at this one later on in the lecture, and we shall carry on. Now, we've got exploration with humans, but what about robotic systems? You know, I've already given away. I'm a child of the Apollo era. I was born in 1968, and I fell in love with astronomy in 1973. I was 5 years old, and I was given this book, and that was it. I was hooked. When I was a kid, this was the best telescopic view we had of the planet Jupiter, and I knew we were going to send robotic spacecraft throughout the solar system when I was a child. I remember the launches of Pioneers 10 and 11 in 1972 and 1973, and Voyagers, of course, in 77. What I never knew is that we'd get images of the type of quality that we've seen. So that's Jupiter from my childhood. This is Jupiter as we see it now. These are images taken by NASA's Juno spacecraft. And this is like a planetary scientist's feverish dream when we look at those cloud and storm systems, some of them approaching the size of the Earth. Not only that, but we've transformed our understanding of the moons of the giant planet. Moons that when I was a child were just points of light in the most powerful telescopes. We have seen worlds of
fire. Io, the most volcanic object in the solar system. Not only worlds of fire, but worlds of ice. We are sweeping over Enceladus, one of Saturn's dozens of moons. And look at this gorgeous view taken by the Cassini spacecraft. We're flying underneath the rings of Saturn, a view that we could only dream about for centuries until the era of robotic exploration. And not only have we seen worlds of fire and worlds of ice, we've possibly seen worlds of life. Because in 2005, as we flew past Enceladus multiple times, we not only saw liquid water spewing out from cracks in the ice, showing the existence of a global world ocean underneath that ice, direct sampling by targeting Cassini through those plumes confirmed that there are organic molecules there. Possible indication that we've got the ingredients for life in a subsurface ocean. And finally, satellite applications. Now, I think most of you are familiar with weather satellites. So this is an image of Cyclone Philin that hit the East Indian coast in 2013. The weather data from meteorological satellites saves tens of thousands of lives every year when it comes down to hurricane forecasting. But what I want to do now is to look at the world in different parts of the spectrum. These are the colors that we can see with our eyes. It's what the retina and our human brain has evolved to see. But what about ultraviolet or infrared? If we can start to detect other invisible wavelengths of light, then we get more data. With more data, we get more understanding. And so what I want to do for my next demonstration is just show you the world in thermal infrared. Now, this is where I'm going to have to chop and change between a couple of things on my laptop, which was not playing up, but deciding to be a little bit like my son can be sometimes. He's 9 years old, and he behaves most of the time, but every now and then he decides to have off-nominal behavior. Note, this is working fine. So I'm just going to transition over to my camera app, which was live, but I think I'm going to have to go cam, open. I can see myself there, and hopefully, yes. Okay. Now, this is the world in thermal infrared. And what you can see on the right-hand side is a temperature scale. You can see the spotlight of temperature in the middle. And it's absolutely fascinating looking at you all like this. Yet you can have a lot of fun with this. One thing I want to point out is you are not seeing heat here. This is detecting thermal infrared radiation. And it's quite interesting on the physics of it. You can analyze the intensity of that radiation by different wavelengths to get a temperature measurement. That temperature measurement in every pixel is being coded with color that we can see, and therefore this is a data visualization of the temperature as measured by infrared emissions from all of you. You can tell I'm a physicist here to try to make sure that I'm being very precise in what I'm saying there. We are seeing the heat, quotation marks. Now, all sorts of fun we can have with this, but why am I showing this to you in terms of satellite applications? Well, what I've got here is I've got a tray, and in this tray, I'm just going to pour some cold water because this is my ocean simulator. And once I've poured in my cold water, I will put my thermal camera onto it before I get a little bit of warm water. And if I pour my thermal camera onto it, I'm hoping you can see there, that should recalibrate. Yeah, that water's quite cold. It's sort of 8 degrees centigrade. So I'm now going to introduce some very hot water in. And you can start to see we've got a much more dynamic system now. Okay? You can start to see how we're getting currents driven in the water by temperature difference there. You can see the cooler regions, you can see the warmer regions. Of course, we're getting mixing there, but I deliberately introduced a small amount so we didn't swamp it all completely. There's an awful lot of physics going on there. Now, that's what we've done with a thermal infrared camera here on the surface of the Earth. The space-based version of this is called a scanning radiometer. And what I'm now going to show you is 11 years worth of data from British-built instruments that have been looking down at the Earth from space, and specifically
at the oceans of our home planet. This is an incredibly beautiful data set. On the left-hand side, you've got time. On the right-hand side, you've got temperature of the Earth's oceans. And we're going to take a bit of a tour here. First of all, you can see just how fortunate we are in the United Kingdom, because from our latitude, we should have the same sort of savagery of weather that we get in northern Canada. Hot summers, really, really cold winters. But it was the Gulf Stream, the warm water current, that keeps us much more temperate. As we move down towards Antarctica, I am astonished every time I look at this video, because you can see how Antarctica as a continent almost doubles in area every Antarctic winter during June and July with that seasonal ice. And now, let's change our perspective to look at the equatorial and tropical regions. You can see the powerhouse effect of ocean currents driven by differences in temperature. They are major drivers of our planetary weather system. And it is not just measuring sea surface temperature that we can do. There is an armada of variables that we are measuring in real time from Earth orbit. We can do it for oceans, we can do it for land, we can also do it for our atmosphere. What you're going to see now is data taken from space of nitrogen dioxide, a really nasty pollutant gas in our atmosphere over New York. And I think you can guess when I've picked March what's going to happen in the summer of 2020 during lockdown 1, dropping down to almost zero. And I could show so many different data sets with so many different atmospheric contaminants. The point I'm trying to make is that more than half of the climate change variables that are absolutely essential to monitor, we can only do at the cadence and resolution that we need from platforms in space. It's like having, I don't know, it's like you've got a patient in intensive care, and you can have all the medical interventions you want. If you do not have the instrumentation monitoring that patient in real time, then you're going to be hamstrung in what you can do. Okay? That is what our armada of Earth observation satellites are enabling for us in terms of understanding the climate issues, understanding the environmental issues, and coming up with solutions. And lastly, space is hardwired into all of our ways of life at the moment. In the top left, I've got a representation of telecommunications satellites, relay satellites that have made Sky TV and global media and news communications a reality. On the bottom left, I've got the satellites that are giving us navigational capabilities, so GPS or Galileo. Now, most people associate them with our phones, and, you know, if I'm using Google Maps, they enable me to go from one place to another. Or if I'm dialing up, you know, I'm getting some food delivered for me on some food dialing app, you know, you're using your navigational capabilities. It goes far beyond there. The atomic clocks on our GPS satellites are the most accurate ever built, and they are used to timestamp every international bank transaction. They are used to regulate our power grids. Turn them off in the United Kingdom for a day, and the cost to the UK's economy would be in excess of £1 billion per day. Okay? This is hardwired into the way we live our lives, our space capabilities. And on the right-hand side, this is a satellite sector that generates vast amounts of revenue. The figures I've shown there are from the global satellite industry going up to 2014. And if you look on the right-hand side, that figure of 200 odd as a bar is not $200,000 a year, it's not $200 million a year, it's $200 billion a year. And as of last year, that figure is $400 billion a year. Space makes money many times over. That dwarfs the budget of all of our civilian and defense space entities put together. And it's giving us critical capabilities that we need. In the United Kingdom, our space sector is arguably our best kept secret. It's worth £20 billion per year, and it's employing nearly 50,000 people. And more fundamentally, nearly 20% of this country's GDP, so for any economists here, in excess of £360 billion a year is critically dependent on our services from space. And so to summarize the importance of that, I'm delighted to share with you my title slide. It was taken by the photographer John Carmichael. And the reason I brought it together with you is A, it's incredibly beautiful, but it summarizes everything I've been saying in a nutshell. This is not a photograph taken from space. This is taken of an eclipse in 2017 seen in the United States from a commercial airliner at 39,000 feet. So you don't have to be an astronaut to be connected to space. We are all connected to space. That's why I wanted to show you the view if you're lucky enough to be flying in an airliner when there is a total eclipse, as there will be later this year in the United States if anybody is going in April. But secondly, we look at the beauty of what you see in that image of the eclipse, and we can see how astronomy draws us, but we look down and we have this amazing perspective of our home planet. So I hope that this slide and this particular image resonates with what I've been trying to tell you, which is quite fundamentally that space is not just part of our critical national infrastructure, space is part of our critical societal infrastructure. Space is no longer a nice to have, but space is a must have. Now, that's my overview of what we have done in space thus far. But what about the future? Well, there are challenges and there are opportunities. This, to my mind, is the most exciting time in space since the 1960s. But it's also the most challenging. And I want to go through the reasons why. I would split it into a few categories. The first opportunity and challenge space is best shown with this animation. Now, this is data that has been taken from Earth observation satellites, meteorological satellites, that have been up there for 20 years. But 10 years ago, you could not have made this data set, because what we've done here is we have combined the visual imagery, but using high-performance computers, we have stripped out the cloud cover, we've introduced data on smoke, sea salt, and dust, because these are what are called nucleation centers in the atmosphere. So they are centers around which water vapor can condense. Now, I look at this image, and it's incredibly beautiful. It is like a visual lava lamp. But in a scientific data set, where you see beauty, there's complexity, there's understanding. And that can be revolutionary understanding. The point I'm trying to make here is that now, with the advent and the explosive development of high-performance computing, of AI, of machine learning, of quantum computation techniques, they're not all the same. I'm not sort of like banding them all together. But these capabilities are going to transform what we can do in terms of the volume of data we're getting in space and making it useful for us. It's an opportunity, but it's a challenge as well. Secondly, what we call mega constellation. Now, what you're seeing here is a visualization of thousands of satellites in low Earth orbit. This is what Starlink satellites are like. And the reason they are being sent up there is that if you've got networks of hundreds or thousands of satellites, Starlink or OneWeb, you enable global connectivity on internet using devices like this without having a huge radio telescope or satellite receiver, okay, or even just a small satellite receiver in the case of Starlink, for the 3 billion people on this planet who at the moment are unconnected to the internet. Why is that so important? Well, to my mind personally, for future prosperity, you need 4 things. You need access to clean water, you need access to food, you need access to education, and you need access to data. What we have seen throughout human history is that getting those right and the data access, that's where you see revolutionary breakthroughs in the advancement of the human condition. And so the potential of these mega constellations of satellites is absolutely profound. But there are challenges as well. And those are the challenges of orbital collisions. What you're going to see here is a visualization of what happened in 2009 when the Iridium-33 satellite, a SATCOM satellite, collided with a dead or defunct Soviet reconnaissance satellite, Cosmos 2251. They hit each other at a combined velocity in excess of like 9-10 kilometers per second. They showered thousands of bits of debris into multiple orbital inclinations and multiple altitudes. And those bits of debris stayed up there for years and years and years. Now, why is this so worrying? Well, when you look at the velocity you need to stay in low Earth orbit, 8 kilometers per second, at those velocities, a piece of debris the size of a 1-pound coin would hit you with the kinetic energy of a Land Rover traveling at nearly 100 miles an hour. And if you've got thousands of these bits of debris spreading out, you've got thousands of other satellites that can get affected. Now, this wasn't so much of a problem back in 2009, but space has got incredibly busy incredibly quickly. I remember back in 2014 or so, teaching some of our undergraduates, and back then there were about 1,000 active satellites in low Earth orbit. As of now, there are more than 6,500 and a total of nearly 20,000 objects in low Earth orbit. You can see them visualized here. What's causing the explosive growth in these numbers are the mega constellations. So in all of this swarm of satellites, I'm now going to subtract all of them except for the Starlink satellites, and you can see that the Starlink satellites are making 2/3 of that cluster. Now, I am not Starlink bashing here. I could say the same for OneWeb with their hundreds of satellites. The point is, space is getting very, very, very busy. Now, that's the active satellites. If we introduce the bits of space debris, more than about 2 or 3 centimeters across, we've got millions of pieces here. And our worry is that we might render, if we're not careful, the entire orbital environment unusable, a plastics in the ocean analogy, unless we do something about it. And what I'm delighted about is the United Kingdom is taking a global lead in trying to set standards of best practice. What do you do with a defunct satellite? Do you bring it back down to Earth? Do you deorbit it? In a regulatory way, but also in terms of technologies. And this is one of the big challenges that we face. And the final, again, challenge or opportunity is sort of encompassed by the next couple of slides and then a couple of more things I want to tell you. What you're seeing here is not footage from the International Space Station. This is footage from the new China Space Station. This, not the ISS, is currently the most technologically advanced structure for humans in Earth orbit. And China's program has gone at an incredible rate in the last 10 years. You can see on the top left to the top left to the bottom left, you can see Wang Yaping, so China's second female astronaut and first woman to do an EVA, a spacewalk, in 2 generations of China's space station, separated by only a few years. You can see that technological difference. On the right-hand side, you can see China's first mission to Mars was a combined orbiter rover lander, and it was successful. This is the Tianwen-1 lander and the Zhurong rover taking this astonishing selfie in Utopia Planitia. And this is not just a pattern that's being repeated in China. We have seen India's successes. We have seen the successes in the United Arab Emirates and a whole range of other countries. Space is becoming more dynamic, more international, more inclusive, and more competitive, which is a challenge space and an opportunity space as well. I want to take a pause to focus now on the planet Mars, because many people ask me, what is so fascinating about Mars? And this particular diagram, we're going to go around in clockwise from the 1 o'clock position, is my attempt to tell the story of Mars in 1 minute. For hundreds of years, we've looked at Mars, but the best telescopic views are what you can see at 1 o'clock. We saw a planet that had an atmosphere, a planet that had polar caps, it had features on the surface that seemed to get bigger and smaller with the seasons, and it rotated around its axis a little bit longer than the Earth, 24 hours, 37 minutes or thereabouts. So this is a world that reminded us of Earth. And there was so much projection that went onto this in the 18th and the 19th and the earlier 20th century. But when we sent our first spacecraft successfully to Mars, Mariner 4 flying by in 1965, Mariner 9 going into orbit in 1971, and then follow-up missions, we saw that Mars is a world that in some ways is incredibly moon-like, but in some ways shows us tantalizing clues that that wasn't always the case, and that in the far past, it may have been much more Earth-like. So going around to the 3 o'clock position, we've got the largest volcanic structures in the solar system. There you can see Olympus Mons, 25 kilometers above its mean datum, and with a caldera at the top, a crater at the top, 65 kilometers wide. This is a volcano the size of France. On its left, again at 3 o'clock, you can see in the northern hemisphere, you can see a vast ice crater where you've got a frozen lake in Korolev crater in the high Martian Arctic. Now, Mars has got an atmosphere, all right, and it is dynamic enough to generate dust devils, as you can see at 4 o'clock from the surface. But don't be misled by that imagery. Mars's atmosphere, it might look like an Earth desert, but it's the same atmospheric pressure as the altitude that Felix Baumgartner jumped at. If you look at that 5 o'clock image, 6 o'clock image, 100,000 feet above the Earth. If it wasn't for the dust in the Martian atmosphere, it would not look anything like a desert on Earth. It would have a black sky, and it would look like a much more lunar appearance, but with sand on the surface. So if you were to pour liquid water on the surface of Mars right now, it would simultaneously boil away and it would freeze. Liquid water can't exist stably. But when we look on the surface of Mars at both a micro scale and a macro scale, we see that this wasn't always the case. Look at 6:30, 6:45. We see sedimentary rock layers from our surface rovers. At the 7 o'clock position, covering an area of thousands of square kilometers, we see evidence of ancient river systems. So all of this tells us that 3.5 to 4 billion years ago, Mars almost certainly was warmer, wetter, with a denser atmosphere. It had an ocean covering its northern hemisphere. And at 9 o'clock, we think we know why it's lost its atmosphere. The planet losing its magnetic field and therefore having its atmosphere stripped away by the solar wind over billions of years to see the desert world that we find now. And most tantalizingly, in our search for life, we are looking for evidence of gases that might be produced by biological activity. And we have detected methane concentrations in its atmosphere. So at the moment, our search is for whether or not life ever got started on Mars. Now, no spacecraft has yet gone to Mars and brought samples back to Earth. But we have got samples of Mars here on Earth. What I've brought with me, and again, you can have a closer look later on, are samples of meteorites that are confirmed as being. In the case of this one, I've got my lunar meteorite. This is NWA 8687. And we know that this is a lunar meteorite because we can look at the mineralogy, we can look at the ratio of certain isotopes of certain elements, and they matches the Apollo samples. And here, I'm actually holding in my hand a sample of the planet Mars. This is from a meteorite that landed in northwest Africa and was discovered by a colleague of mine in 2014. This is NWA 12564. And here I've got some grains from a very famous meteorite that's been confirmed as Martian. This is the Nakla meteorite that fell in Egypt in 1911. Now, the fact that I'm holding pieces of Mars in my hand, it makes what's left of the hairs on the back of my neck stand on end. But why? Because when we look specifically at 3 of these Martian meteorites, including Nakla, with electron micrography, magnifying hundreds of thousands of times, there are features which some astrobiologists of world-class reputations are saying are evidence of ancient life having existed and created these features. Now, the human in me, well, the romantic in me, wants to believe that I've got evidence of ancient Martian life here in my hands. These are samples of the Nakla meteorite. But the scientist in me also thinks there are non-biological ways of producing similar features as well. We can't tell. And in science, as Carl Sagan, I think, said, who a very famous astrobiologist, I think, here in this very lecture theatre, you know, if you've got an extraordinary claim, you need extraordinary evidence. And if I want to use this to analyze whether or not life ever existed on Mars, this has been contaminated by lying in the desert in northwest Africa for thousands of years. I need to get pristine samples of Mars, uncontaminated, back to Earth. And that's what our focus is. So right now, on the surface of Mars, we've got the Perseverance rover. And there it is with the Ingenuity helicopter on the surface of Jezero crater. NASA and ESA chose Jezero for this mission because Jezero is a crater which looks like this at the moment, but billions of years ago, this is what we think it looked like. And what Perseverance is doing right now on the surface of Mars is it is going to various sites and it is caching dozens of samples in small tubes that a combined NASA-ESA recovery mission towards the end of this decade will fly to Mars, bring back to Earth, analyze in our laboratories, and maybe unravel whether or not life ever got started on the surface of the red planet. 2 final points before my conclusion and opening for questions. I hope there is a voyage of discovery and human and life understanding that I've outlined here. But many people argue, well, you know, why do we studying other planets? What I've done here is I've got Venus, Earth, and Mars represented next door to each other to scale. These are three of the sun's children, in effect, in the inner solar system, that billions of years ago, the evidence would suggest were very, very similar. Why did they follow such wildly divergent trajectories? Why did Venus become a runaway greenhouse hellhole of a planet? Why did Mars lose its atmosphere? Why was Earth so special? This is comparative planetology. And in terms of the understanding of aerosols in the atmosphere, in terms of the role of other gases in the atmosphere and surface features, our understanding on Earth has been massively accelerated by discoveries we've made looking at other planets in the solar system. And one more point I want to bring up. With the advances in robotic technology, many people say to me, you know, why are we bothering sending humans into space? Well, I want to summarize it by talking about the Apollo 17 mission. I remember this. December 72, I was 4 years old, watching it on a black and white TV, the last human mission to the moon, with my childhood hero, Jack Schmitt, as one of the surface crew, the only geologist to fly to the moon. On the right, you've got Perseverance. In its first 16 months of operations, Perseverance covered the same amount of ground as Jack Schmitt and Gene Cernan did on the lunar surface at Taurus Littrow in 3 days. By the time we build, flight qualify, launch, get to our destination, any robotic system, it is obsolete. There is no system at the moment robotically that has got anything like the capability of a trained human operator. So in our future exploration, we'll be having a synergy of robotic systems and humans. And boy, is it exciting times that we have got lined up ahead. I think many of you are aware of the Artemis 1 mission, which was the flight around the moon of the Orion capsule that on future missions will take humans back to the moon for the first time in more than 50 years. And it's not just a NASA mission. There you can see the ESA logo, European Space Agency as well. Europe builds the service module for the Orion spacecraft. Because in our return to the moon, we're not going to be going for 2 to 3 days. The idea is we're going to build a lunar orbital space station called the Gateway, and we'll be having extended surface operations at the South Pole region of the moon. The idea is, can we get an extended human presence on the moon to do science that we can't do on Earth and prepare us potentially for human voyages to Mars? It's an incredibly exciting time. And these are the people that will do it. On the left, you've got Christina Koch and the rest of her crew. You've got Jeremy Hansen, you've got Victor Glover, and you've got Reid Weissman. 3 NASA astronauts and a Canadian astronaut. Space is becoming more and more international, more and more inclusive. Top right, the United Arab Emirates Space Agency. I've been privileged through UK government to work with them over several years, and their progress curve has been like this. Their second astronaut, Sultan Al Nayadi, just returned from 6 months on the International Space Station, becoming the first Arab astronaut to do an EVA, a spacewalk. The UAE's space expertise in human spaceflight now equals the UK's. On the right-hand side, Noura Al-Matroshi, one of their newest astronauts. I fully expect to see her in lunar orbit by the end of this decade. And I think the challenge for us in the United Kingdom is, do we have the ambition to go for it? Certainly my agency and the European Space Agency, we have bold ambitions. And on a personal level, when I look at our 3 British astronauts that we currently have in the astronaut corps, you know, our shared ambition is for them to be explorers on behalf of all of us. Now, we have challenges in our way, but this is our goal. And to conclude, when they go, whoever the next generation of astronauts are, this is the view they will have. And this is the view that they'll be sharing with us vicariously as participants. What you're seeing here is a view from Lunar Reconnaissance Orbiter of the Earth rising over the moon. This is not a souped-up image or a composite image, as seen by the human eye. So they'll be seeing this view, they'll be sharing with us. And I want to conclude with this slide because, you know, people have said that the most important thing we've learned in space exploration is just how very special our home planet is. It's our view of the Earth. When I look at this view, it strikes me that Earth, of all of the sun's children, is unique. Because this is a planet on which life has not just survived, but life has thrived. Not for millions of years, but for billions of years. Life on Earth has fundamentally changed the geology of our planet, the oceans of our planet, the atmosphere of our planet. These are changes that are detectable at astronomical distances. If I was an alien visitor to our solar system, I would ignore every one of the dozens of moons of the outer gas giants, and you'd come hot-footing it here to the third rock from the sun. Okay, this is a very, very special place. And if we are to safeguard it for future generations, then our space capabilities, they are no longer a nice to have, but they are a must-have. With that, I'd like to thank you all. I have bust my time limit by 6 or 7 minutes, so I'm sorry it was a slightly extended lecture. I hope you found it of interest and maybe a little bit provocative, and I'd be delighted to have the opportunities to answer any questions that you now have. Thank you very much, everyone.